Hello everyone. We've been talking about Hermite interpolation in the last few videos, and we have found the explicit expression for the basis elements in terms of the Lagrange polynomials, and now we will work out an explicit example and try to understand how everything works. All right, so let's work out an example. So the example is that f of x is equal to sine x, and my nodes are at 0 and pi by 2. Okay, so how many nodes do I have? It's 2. So what is my value of n? It's 1. And what is the degree of my polynomial then? It's twice n plus 1, which is 2 plus 1, and that is 3. All right, so I'll have a degree 3 polynomial. That's my prediction. And let's check now. Let's calculate the polynomial. All right, so my x0 is equal to 0 and x1 is equal to pi by 2. All right, now my f of x0 is equal to sine 0, which is 0, and f of x1 is equal to sine pi by 2, which is 1. Okay, and now I have to match the derivatives as well. F prime of x0, so the f prime of x is nothing but cos of x, and cos 0 is equal to 1, and f prime of x1, which is cos pi by 2, and which is 0. All right, so we have these datas here, we have these informations, and now we have to use that and find the polynomial. All right, so how will my polynomial look like? So my polynomial p twice n plus 1 will be p3, as we have calculated that. p3 of x will be f of x0 h0 of x plus f of x1. So I have to first match the values of the functions. So h1 of x plus f prime of x0, which is equal to h0 hat of x plus f prime of x1 and h1 hat of x. All right, so this is the most general form when I have two nodes, when I'm doing Hermite interpolation. All right, so now we know that f of x0 is equal to 0 in this example, so this term would go to 0, and f prime of x1 will go to 0, then this is 0, and these two are 1. So all we will be left with is something like this, h1 of x plus h0 hat of x. Okay, plugging in the values from the red box. So this is what we will get, and now let's calculate these h and h hats. Okay, so let's calculate h1 of x first. h1 of x, according to this formula here we can write it. So this would be 1 minus 2 x minus x1, and you will have L1 prime of x and L1 square of x. So we have to calculate the Lagrange polynomial, right? So L1 of x will be x minus x0 divided by x1 minus x0. All right, if you plug in the values, this would be x minus, what was x0? x0 was 0, and x1 was pi by 2, so it was pi by 2 minus 0, so it would be 2 by pi into x. Okay, I should not use the bracket, otherwise it will be confusing. So 2 by pi x. So if I want to calculate L prime, because I'll need L prime, the derivative of L, L1 prime of x, that would be nothing but 2 by pi. Okay, now plugging in the values, what we will get is h1 of x will be 4 by pi square x square 3 minus 4 by pi x. So what we are doing, we are just plugging in all the values here. X is equal to pi by 2, x1 is equal to pi by 2, plugging in the value here and plugging in the value here. So if we plug that in, we get this form for h1, and you can already see here it's x squared times x, so it's an x cube. That means it's a degree 3 polynomial. I mean, at least a degree 3, and we will prove that now. I mean, we will see it in very soon. So what's the next one? We have to calculate h0 hat now. Okay, so let's calculate h0 hat. So h0 hat of x from the formula is x minus x0 L0 square of x. So what is my L0 square? So my L0 of x is equal to x minus x1 divided by x0 minus x1, and this, if you calculate, it would be x minus x1 was pi by 2 and this was 0, and minus pi by 2, and this would be nothing but 1 minus 2 by pi x. Okay, and now you plug it in back here, back in this formula, and put x0 is equal to 0. Then you get h0 hat of x is equal to x times 1 minus 2 by pi x whole square. So if we add these two, okay, let's mark it in a red box, and if we add these two red boxes, we will get the polynomial. And my polynomial looks something like this. P3 of x is equal to x 1 minus 2 by pi x whole square plus 4 by pi square x square 3 minus 4 by pi x. Alright, so we have got our polynomial, and let's check it with a graph. So we were interpolating sine x. So you all know how to plot sine x. So it would be something like this and this, right? And my two nodes, okay, let me draw it maybe properly, something like this. And my two nodes, okay, let me use this orange here, this one and this one, 0 and pi by 2. These were my two nodes. And if you calculate, if you plot this P3 here, so that will be something like this. So you can see that okay, you can check it by yourself by running a code, but what you can see from here is that with only two nodes, these orange ones, you have got almost a perfect answer. All right, and that is the, I mean, the reason behind it is that you are doing Hermite polynomial, Hermite interpolation, that makes you not only to make sure that the values of the functions matches here, but also the derivatives. That means that the directions, so the direction is this and the derivative is this. So when you are matching that as well, then it makes sure that your polynomial, I mean, is a better interpolation, I mean lesser error. And this is the end of this chapter. And what we did, that we got the basic idea of polynomial interpolation, and then we solved it with van der Waals matrix, and then we solved it with Lagrange and Newton's basis, and they have both had their own pros and cons. And then we talked about interpolation error, and then we talked about a special phenomena called Runge phenomena and solved it with Chebyshev nodes. And then we went to a special case where it was even better, where we not only did for the values of the function but also interpolated the function at the value of the derivatives as well. So which is called the Hermite interpolation. So that's all we covered in this chapter, and this chapter will be very important for the rest of the course. So I hope you enjoyed it, and please let me know if you have any questions. Thank you so much.